Okay, well, hello everybody. Good afternoon. My name is Charles Noren. Today I'm going to be giving a presentation about the work that I completed this summer. And I'm an intern with the Autonomy Incubator. This will be my first time returning, second internship overall, and I worked closely with Derek and the AMA guys and did some work on in-space assembly last fall. So this is like a continuation, but almost a separate, kind of a parallel branch to the efforts that I've been working in the in-space assembly thus far. So I'm going to go over a lot of what has been done, kind of the methodology, looking at the capabilities that have been designed, and then talk about some of the next steps and some lessons that I've learned over my time this summer. So some quick information about me. I go to Texas A&M University. I'm an aerospace engineer. I'm a senior. I'll be graduating this fall. And I started back in May, and my last day is going to be this Friday. My goal for this summer was to support a hardware-in-the-loop reference mission for in-space assembly. You guys are very familiar through the sprint slides with some of Derek's work. It was also presented in my presentation last year with using the arms, the different UR3 arms. And my work is actually going to hopefully seamlessly interface with that work when we're completed. The idea being that we'll have a fully robotic team being able to locate some of the trusses that he's been working with and then be able to place them in a more particular organization or orientation alongside the other trusses. So with that, I'd like to talk a little bit about in-space assembly as a whole and why it's important. I picked a lot of these photos due to the fact that they actually do have a lot they have a lot in common with the complete idea of in-space assembly. The first one being that humans actually do most of our in-space assembly work right now. It's a lot of times human-oriented. You guys have always seen spacewalks, seen pictures of spacewalks, and right now we're putting our astronauts and a lot of their sisters in danger when they go into space. There's a lot of dangers in space, and sometimes in-space assembly can be very complicated, taxing work. So the idea is that making it more robotic, we might be able to kind of improve safety or be able to help assist in these endeavors. So in-space assembly really arises from the idea that we can't launch exactly what we want all in one launch vehicle. That means sometimes it's too heavy or too big. Imagine trying to design some sort of rocket that could be able to launch the International Space Station in one go. It'd be extremely difficult to do so. And so what in-space assembly hopes to achieve is to be able to break down such launches into smaller sets, whether that means there has to be less mass per each rocket, or maybe it can't collapse any farther, so there needs to be set into different pieces. In-space assembly is meant to address both sides of the issue. And there's been many different approaches and actually many different added topics the further we develop this idea. Originally in-space assembly really kind of started with docking and docking maneuvers back in the Gemini program and Apollo programs. And then today we have objects such as the James Webb Space Telescope, which you guys are familiar with. There's been a lot of media coverage lately that has the James Webb in its kind of deployed form, all folded up so it can fit inside of a launch vehicle, and then it actually kind of an origami style unfolds, and that helps us be able to deploy something that has a lot larger volume. For what we're looking for in the Ramses mission, actually kind of falls between this element-to-element mating section and the modular assembly side, due to the fact that the trusses are very similar in kind of shape and structure, and they need to be oriented in a very similar way. And these further sections of in-space assembly, the complex assembly and assembly from parts, generally refers to like non-homogeneous parts, or maybe some sort of fluid connection line, electrical connections, different kinds of assembly that requires a lot of dexterity and work that way. So one type of reference mission which might be useful for robotic or autonomous in-space assembly could also be that it's really far away. The James Webb is almost 1 million miles away, so sending an astronaut team up there to help try to build it isn't really practical. Or how about maybe an in-space assembly approach around Mars? That would be extremely impractical to send an astronaut team all the way out there to just assemble something and come back. So what if we had a set of robotic groups, maybe a course aligner, such as the Cirrus module, and then maybe what I like to call that course kind of tug style, that it has to go out and grab something, and then it needs to deliver it to some other, maybe some other placer, what I like to call the course find placement, which would be this object. So one of our items is floating out in space, this truss structure, and we want to be able to go grab it such that our coarse fine operator can then place it into a better orientation. So our tug travels out to the object, aligns with it, goes for the capture, then brings it back over to the coarse fine, hands it off, and this handoff is then, the object, the coarse tug ends up moving away, and then the entire maneuver is then performed by the coarse fine operator. So that would be the style of mission that you could see and that we're trying to emulate here in the Autonomy Incubator. For us, this coarse tug, the Cirrus, is going to be TankBot. It's a 6-wheel drive differential vehicle. And then the coarse fine maneuver would be more like the UR3 arm that you guys can see downstairs that grabs the trusses and places them. So that's the handoff. That'd be the idea, but with full scale size. So TankBot would hand it off to the UR10, and the UR10 would place. So the mission overview is really summarized kind of in this photo. The idea is that TankBot will be able to do the coarse alignment by capturing a truss, then delivering that to a specific place around the other trusses, such that a UR arm that's nearby would be able to manipulate it and put it in a much finer orientation. So some of the required capabilities of this vehicle is that it must be initializable, must be able to be communicated, must be able to be started remotely. The idea is that it could be able to communicate with us, be able to transfer information, not only for safety and mission critical needs, but also just for efficiency reasons. We want to be able to find the truss and then be able to drive to align with it, which means get ready to capture and then officially capture the truss. Once we've done that, we'll take it with us somewhere, not dropping it, and then we'll hand it off to some other agent inside of our autonomous system. So it's kind of interesting because this kind of set of 9 capabilities is also very similar to the UR arms and how they work. You know, the UR arms initially they have to be initialized with a plan. They communicate with us as researchers that says, you know, their state and what they've seen. They look for the truss using the camera on top. Then they have to align with the truss. They go in with the move Cartesian to grab it. And then once they've captured, they've gripped the truss, they then deploy it in a position, and then they, you know, basically retreat from the area. So it's a very similar style, but you can see how there's this kind of pervasive overall idea or behavior that kind of pervades inside of in-space assembly. So let's talk about kind of the overall brain of the organization, the controller that was designed. I looked at a couple different papers. I spoke with Javier. He gave me some great ideas. And the first idea that I really thought about was some sort of path-based controller, some sort of path-based trajectory generator. I was inspired by a paper that I read that Javier actually sent me that was talking about utilizing this concept of a virtual vehicle that would then be able to be tracked by your real vehicle. So it'd be almost like you're playing follow the leader a little bit. And the idea is that a vehicle with a fixed velocity would try to minimize the heading difference or the orientation it has, while also kind of trying to minimize the lateral offset. So assuming something like a path frame, if I'm traveling along a line, lateral offset being if X is along the line, Y is to either side. So we're trying to minimize those 2 items while also trying to minimize the difference in orientation. Basically try to converge kind of like this NASA swoosh that you can kind of see going on here. Now, the one thing that is kind of interesting about this particular implementation of the controller is that it's fixed velocity, which means that we can't force a temporal constraint. It can be generalized to a differential velocity to help with some of those temporal, you know, trying to have both the objects reach at the same time. But due to the complexity and what we're trying to do, it wasn't necessary for this particular application. So I designed it as a digital trajectory controller. Basically, it's trying to do a sample approach to trying to sample a continuous time trajectory controller. And then I implemented it in MATLAB just for a proof of concept, and then Python to be actually used by the rover. Additionally, I've had a little bit of work in the robotics fields, and a general kind of rule of thumb is always be able to follow a line if you can. So I designed a linear trajectory follower just as a way to be able to test on the rover or be able to work with it as a type of implementation failure. Maybe that could be anything from trying to retreat path or some sort of recollection, but linear trajectory followers, really good. So for our hardware, we have a setup with the AndyMark Tilerunner. This is the 6-wheel differential drive vehicle. It means that it's actually controlled kind of like a tank, if you've ever seen it. Basically, it's not like your car where you steer with the steering wheel and then you make a turning radius that way. It's actually, each side is independently controlled. So you put power to one side, you'll turn in that direction. You put power to the other side, you'll turn in the opposite direction. Kind of like a skid steer design. So this particular vehicle had to be modified to be able to actually manipulate the trusses. So a set of actuating tusks were installed, and we'll get to those in a second, that had to be able to determine whether or not we had captured the truss, due to the fact that we needed some sort of recognition. If we're going to be able to say that we're manipulating something, we need to recognize that. So the sensor went in there. And that actual touch sensor is controlled by an Arduino microcomputer. And then our mission computer, kind of think of it as the higher level logic controller, is the Intel NUC that you see on top. And then the flight computer is a Pixhawk itself, and then the actual ESCs are basically how we determine how much power we're going to give to each side, or these Rev Robotics ESCs. So these are the NUC here, Pixhawk on the back side. You can see the GPS module on top, and then the ESCs themselves. Each one of these things actually has error or has communication problems inside of it. So there's a lot of hidden troubles that are kind of hidden within inside of these that we have to work through as roboticists. All the communication, or the mapping, or all these different kind of special features of the robot itself. The tusks themselves were inspired from a robotic vehicle that I helped design at first when I was a student in high school. I saw that we just needed two-position actuation, so we have a two-position actuation system. You can see up in the middle and then down. It's be able to be controlled by the robot when it understands that it has or has not captured a truss. We also have these are the limit switches you can see on the vehicle itself. It's kind of hard to see because it's been sharpied over, but the limit switch is actually depressed when the tusks go down. The actual bar of the tri-truss, as you can see here, we grab one of the ones along the bottom, and we depress the tusks to capture the bar, and when they do, this limit switch will trip, and that's how we'll know what's going on. And I wanted to give a big shout out to Jim Farrington, Jim Plant, and Brian Duvall for their work on that. They really helped me out in the manufacture of the tusks. So this is kind of the meat and potatoes of the whole object, is the software structure and the design behind how the robot actually operates. The goals was to develop this modular architecture that would allow us to swap out controllers, generators, sensors, you name it. That's the entire approach, such that we can have increasing capability as we move forward. We also wanted a lot of redundancy in the system. It's best to have that for both safety reasons, with different fail-safe methods for the Pixhawk itself, and to kind of have some sort of trust, developing trust with, between the different computers. If the mission computer is expecting to receive information, we want to make sure that's happening, and if it's not, then we want to be flagged for it. So vehicle timeouts, if the vehicle isn't responding as expected, multiple arm requirements, arm not being you are arm, but actual arming, which means allowing for motion. And this redundancy is pervasive throughout the entire set. The controller can throw flags, robot monitor can throw flags, the robot itself can throw flags, all of the idea that we can have safety in motion. And then we want interfaceability. In other words, only talk to the upper level. Everything else is kind of abstracted below it. So. With that, this is the actual logical structure. It's kind of daunting. It follows a whole lot finite state machine approach, and these are kind of the 5 categories you can see on the left side. This is the initialization of the entire vehicle. We then move into the actual alignment point motion, followed by capturing, moving to capturing, and then capturing the truss itself, and then the drop and the finalized. So let's get into it. Logical structure. So the initialization happens from a parameter file, .yaml. Allows us to have customizability in what you want to see, whether you want to do simulation, with robot, without robot, with Vicon, no Vicon data, having touch sensors. You can test each and every component independently, such that you can be able to test each one as you integrate them together. The path planner allows for multiple different controllers to be integrated, whether you want the straight linear trajectory generator or the controller that I designed, or maybe one of your own choice. It needs a little bit of refactoring after some structuring changes, but that's going to be later today. Some heavy integration work between all the different types of sensors and all the different types of communication channels, whether that comes from Vicon, which is going to be this stream here, or to the Pixhawk, which is going to be this stream here, and Arduino is included in the parameter file. So all these computers have to talk to each other and eventually develop into kind of a handshake so that they understand where each one is reading or which one each sets, so that the actual robot commander can then move forward with the design. The logical structure then moves to the actual capturing procedures. And I've designed an architecture that allows us to be able to move while still trying to keep track of where we are and how we're doing it, due to the fact that the PICSOC itself does not tell me whether or not we have successfully completed our move. In other words, we move when the vehicle actually moves forward, instead of receiving a message back, which is kind of frustrating. But that's part of the reason why we need to have things like Vicon or independent tracking, and that's why the mission computer kind of keeps the flight computer responsible for what's up. So pre-flight checks are all information, making sure that we have power. Again, it's one of the safety redundancy checks there. And then we plan a path to the alignment point. We go through another round of safety checks to make sure that we're still where we expect to be. We generate a command, move, and then continue forth until we reach the alignment point or default out, not being able to get there. And then the auto timing out on the safety check pass, the idea behind it is that it keeps us honest, right? Trying to keep that motion together. Then we move on to the actual Truss capture of the object. And you can see that there's more complex logic going here. We come in from the alignment point to try to generate a capture point trajectory. And then we go through the same motion as we would go to the alignment point. A little bit of reuse there. And then we have to have our actual capture behavior. How are we going to grip the truss? How are we going to deploy it? And that's going to be through the tusks mechanism. So we drop the tusks, check for trip limit switches, and collect. And then if we don't, we send the reason and continue forth until we time out. The final thing is the actual truss drop, which we need to be able to account for other robots, specifically the UR-10, trying to be a responsible partner in this robotics system. And a lot of this is yet to be implemented. But a lot of the idea is that we're going to have specialized checking for timeouts that structure already exists, and then whether or not we actually have captured the truss or dropped the truss. So that's the idea there. With that, some big lessons that have been learned. Integration takes a lot of time. I've been working on integrating all of the parts. I've had the parts designed since the end of June, and I've been putting them together since July. So a lot of times the vehicle doesn't like to integrate well with itself. So the flight controller operates at too high of a operational rate. Basically, the vehicle cannot respond fast enough to it at the lower level. As well as that sensor integration is critical to autonomous operations. I'm sure you guys heard earlier this week I was having some trouble with the floor. Yes, the floor has come to bite me. It had some sort of magnetic structure inside of it, which meant that I had to basically rewrite how the vehicle interpreted its own heading. And that way, it's all about how this kind of being able to sense one's environment comes into the whole question of autonomy, and why that's important, especially for something like a space-based system, which will have to have a lot of redundancy, a lot of checks, a lot of reflection. And then we don't want to overestimate our lower controller capabilities. Ramp up on the rover is a really long time, but this just goes to show you that whenever you depend on something at the lower level, you need to be able to account for it at the higher level. So my current controller actually has to downsample itself in order to try to achieve a rate that the lower level controllers on board the PICSOC can respond. So with that, I'll take any questions from anybody. And thank you guys for coming.
What competition was your first robot for?
I was a first robotic, actually called First Robotics Competition.
No, I was in it. Which
Oh,
one
cool.
was it?
Oh, fair enough. I was present in 3 years, Rebound Rumble, which is a basketball year, and then Ultimate Ascent, which was a Frisbee year, and then Aerial Assist, which was an exercise ball
That's
year.
my first one.
Yeah, it's pretty cool.
So how well does this work?
Well, that's a good question. So all the parts have to be integrated together. Currently what I have is I've been developing the capabilities kind of in this order of the logical structure. So currently what we can do is we can initialize the robot, we go through all the pre-arm checks, we localize both the robots and the environment. We can then control motion to a specified point. And then once we get to that specified point, if we are in contact with the truss, we can analyze it and say that we have or have not captured it. But we're still working on the reorientation, and if we jump over a point, trying to realign with it. So, yeah.
I have one. What is the latest state on the magnetometer on the GPS and the magnetometer on the PICSOC?
So the magnetometer on the PICSOC is fine. The internal compass, I don't believe, is. which means that when I develop the solution to the motion capability so that we can drive reliably, I basically overwrite its internal compass. And I use Vicon frame and a bunch of frame transformations to let it know its real orientation inside of the Vicon observable frame. So once Vicon observe its orientation, then I can dynamically plan around the fact that its heading is rotating. From that, I can develop which direction I want to travel in. So basically, I overwrite the internals currently on our rover and force it to travel in the direction I want it to travel in.
Great. Thanks, Chase. Well done.